So hello guys, I'm Ritunjay, and today I will be presenting the theory part of this lovely session. So we start by understanding what is machine learning. So according to this book, machine learning is a study of powerful techniques that can learn from experience. And that experience could be in the form of labels. That experience could be in the form of exploration. Like for example, if we give an agent an environment itself, an agent can learn from it, or it could learn from data on its own, like in the case of unsupervised learning. The higher level anatomy of a machine learning model or an algorithm is input, model, and output. So we give some input to the model, and we expect some output out. And there are some knobs that our model essentially tunes in order to get the best possible output that we could hope for. These knobs are technically known as parameters, and in machine learning, we deal with parameters all the time. Now, if we go much deeper into the anatomy part, we found out that there are four main components of any machine learning system. One, and I believe one of the most prominent, if not the most prominent one, is the data itself. Second one is the model. Third one is objective, and fourth one is algorithm. So we will dive deep into each and every one of these components as we move along. So first and foremost, data. So arguably the most important part of learning system. There's no data science without data, right? Came in many forms. For example, categorical data could also be time series data, could also be a real value data, and so on and so forth. There are some potential issues that comes with data itself, which is the responsibility of data scientists to get rid of as much as they can. So one of which is undesired bias, because there has been a huge debate regarding the bias of model, at the same time bias within the data itself. So we should always be mindful of that as responsible data scientists. Second one is train and test distribution shift. So if we put our model in production, it almost always never works as in its vanilla form, and the reason for that, people change and the system change as well. So that is the reason behind we have to update our model on the go in production. I don't know, within 3 or 4 months. That's been an experience with my part. So that is one of the major problem in putting data in putting models in production. And I think let's move on to models. Yeah. So I really like this quote by George E.P. Box. So he says all models are wrong, but some are useful. And the reason for that is because okay, so from what I could get out of this quote is that we may never know what the true model is, right? So we always play with the approximation of our true model essentially. So one can say that all models are wrong, but some of them are useful at some point of time, essentially, right? So the model that you might put into production may be useful at that point of time, but because of distribution shift, it isn't going to be that useful after 4 or 5 months, right? So yeah, that is a good quote that I quite like. So yeah, of course, there are many different types of models. Each one tends to be appropriate for a specific task in sentence, and we insert some prior bias, which we feel that our data inherits. And of course, we have to deal with major issues like overfitting, underfitting, generalization, so on and so forth. Simply speaking, A statistical model takes an input and provides an output. So we have, for example, output denoted as y, and we have a function f of x, which is a model. Objective function, yeah, exactly. So this is one of the major part of the equation of this entire ML equation. So objective function essentially tells our model that where should we move, right? What do you want me to optimize, or at what metric do you want me to improve upon, right? So for example, you are creating a self-driving car, right? So you wanted to minimize uh, the amount of pedestrian that you might hit. So the best possible scenario is you don't hit any pedestrian, right? So these serious ideas can be converted mathematically so that our computer can understand by the means of objective functions. Uh, and oh, of course, objective function goes by many names: loss function, cost function, and so on and so forth, right? And once we have our objective function, we know what our objective is. We can essentially use our optimization algorithm. The most famous one is stochastic gradient descent, but that is not the only one. We can use Adam, Adagrad, and countless others that came by quite frequently, and some of them works in some other settings better than the other one. So we have to be mindful of that as well. But the basic idea is that we are using this algorithm in order to tune our parameters in order to, so that we can minimize the objective function essentially, right? Types of machine learning. So by the way, there are bajillion types of machine learning, but broadly speaking, there are three major ones: supervised learning, unsupervised learning, and reinforcement learning. And supervised learning, as the name suggests, we are supervising our model, right? The way we are doing that is by giving them labels, right? So we give them inputs as well as labels. We tell our model that this input must correspond to that exact label. Or in the settings of regression, we give some continuous values, and we say that given this input, I want this output. So this entire procedure comes under the banner of supervised learning, but that is not the only one, as we've seen earlier. Another one is unsupervised learning, in which we don't have to worry about giving our models labels at all. So the basic idea is that we want our model to learn as much structure as possible by just looking at the data only, right? So some of the really famous candidates under this banner is PCA, non-negative matrix factorization, TSNE, variational autoencoders, and so on and so forth, right? We can also use unsupervised learning and clustering and recommendation systems, and so on and so forth, right? Reinforcement learning. Funny enough, Pierre and I were a part of another session, another series. I think it was the longest one we had the chance of be a part of. So in that series, we go over a really great book by Sutton and Bartow, which is a standard book for understanding reinforcement learning. So what is reinforcement learning? So as I mentioned earlier, we give our model something to look at so that they can understand from experience. In this case, we give them experience by first giving them environment, and we allow our agent, essentially we allow our agents to query our environment as much as possible. And the basic idea is agent wants to know, is it in a good position or in a bad position? So the way to do that is by giving a reward. So when agent is in one position, he wants to know, am I in a good position? So he asks environment where I am. He gives that guy a reward. And from that, he said, should I go forward, or should I leave it as it is, or should I move to the other direction and run away for my life? So that is the basic idea of a reinforcement learning system. There are other types of machine learning subsections as well, right? Types of machine learning as well. So one of them is meta learning, metric learning, few-shot learning, self-supervised learning, contrastive learning, continual learning, and list goes on and on and on. With that brief introduction of the 10,000 view of what machine learning is and what are the subsection of it, let's do something concrete, right? So one of the most basic and most the algorithm that we all learn when we first get into machine learning is linear regression. But in this section, I try to do something different and try to connect it with neural networks, which I believe is going to be fun. So let's first understand linear regression. So here are our four main ingredients, right? So we have data, model, objective function, algorithm, right? Which is our update tool. So data, let's, for example, our classical Boston-Hausen prediction data, right? So it's a tabular data. Now our model, that is our main part. So in this case, so our model is going to be linear. So in this case, W is our matrix, which gets multiplied or matrix multiplied by our inputs in order to get the output which are as close as possible to our outputs, our true outputs, right? So the way to insert that idea is through the means of objective function. So objective function is trying to minimize the mean squared error, essentially. So the mean square difference between our predicted y and the original y. And once we know the exact value of it, what are we going to do with it? So we wanted to update our weights in order to minimize our objective function in this case. So way to do that is using the algorithm part, which is the update tool. Here we are using stochastic gradient descent along with learning rate alpha. And at each iteration, we essentially update our weights. Here I denoted weights as theta. By the way, that's one more thing that I would like to highlight, that there is a really big difference between notations, I think. So for example, some of them mention it as W, some of them it mentioned as phi or theta, sorry. Some of them, yeah, like I think that pretty much it. I will come up with more notations as we move along, I think. So what we get out of doing this entire thing is we have a linear regression model in which at each iteration it tries to make a best linear fit from the data we have, essentially. So in this case, our data has a linear relationship, right? So that is one of our assumptions. But what if our data is non-linear? Like in this case, so if we were to fit a linear model, we are not going to get a better job out of it, because as you can see, the data is non-linear, right? So the way to deal with is to go back to our model laboratory, if you will. So we have the original linear function, right, which is W transpose X. What we can do in order to inject non-linearity is by transforming our X in such a way that will make our outputs nonlinear. So the simplest way to do that is to use something called a basis function. And the most popular basis function is polynomial basis function. So as you can see in polynomial regression, what we do is we basically create a matrix in which each columns represent a particular degree of polynomial. Like for example, if we have x, then the other one is going to be x square and x cube, so on and so forth, right? So the advantage of introducing these new features into our data is that we can now address the or we can now inject non-linearity into our model. So even though the model is still linear, but we can now model non-linearity because of this introduction of basis function. So that is quite a powerful idea, which is apparent as we use that idea inside this data set. So as you can see, the brighter line fits much better than the linear one, and the reason for that because we have injected a polynomial basis function into it, right? So similarly, we can manipulate our model library as we want. Like for example, in order to get rid of overfitting, we can add regularization, which leads us to ridge regression and lasso regression that you might have heard of. In order to take into account the classification problems, we can first of all convert our linear outputs into probabilities. The way to do that is to use either a softmax or a sigmoid function, right? And we can, instead of using MSE loss, we can use cross-entropy, right? So one might wonder, why do we even need neural networks? Because like we can essentially model nonlinear data by just what we have, right? So for example, by just using a linear model and just injecting basis function into it, right? The biggest advantage of neural networks that I think is that they allow you to have adaptive basis function, right? So the problem with what we have up till now, so the problem of using polynomial regression and so on and so forth, is that we have to specify our basis function beforehand. So that basis function may not be useful in other data sets, right? So also you can essentially understand the relationship within the data in smaller dimensions. But what if we have 10,000 dimensions, right? At that point, you will be lost. You don't know what relationship that our model has, right? So what neural networks cleverly did is that they can find the basis function which is best for our data. There are many names to this procedure. One of them is representation learning. So you might have heard of this sentence that neural networks can do representation learning, and that is one of the reasons behind the success of neural networks. They also goes by many names, one of which is feature learning and experimental learning, right? And of course, we have universal function approximation, and we have a really good capacity when it comes to using neural networks, and it is extremely flexible. We can add or we can construct a really good architecture in order to facilitate our model, essentially, right? So now that we know why do we need neural networks, just so that just to recap, we need neural networks in order to create features that are best for our data sets, right? So that we can have a good classification or we can have good regression, right? But how can we go from linear regression to neural networks, right? So that is a really good question. If we look closer, we can find out that linear regression can also be represented with neural networks diagrams, right? So as you can see, we have these input layers, right, which is our axis, and then we take the linear combination out of it, and then post it out as an output layer, right? So if we look closer, what we can find that it looks exactly like neural networks. The only difference is that our activation function are linear, right? So in this case, we take the linear combination and then we inject it to our activation function. Here in this case, our activation function is just a linear function. So that which means we end up with the linear combination, just like what we have in linear regression, as you can see, right? So there is another name to this linear regression. It is known as linear neural networks, and the linear because our activation function are linear, right? Now, how can we go from linear neural networks to MLP? So the simplest idea is to just just go deep. I think I should add a matrix meme into it. That would be more funnier. But yeah, so what we do is to add multiple hidden layers, and most importantly, we have to use non-linear activation functions. So one of the most famous one is ReLU, but historically people have used sigmoid and tanh and step function as well, right? So that is the reason behind neural networks. That is one of the reasons behind neural networks is so powerful, because it has activation function that is non-linear, and it can model a basis function on the go. You don't have to specify it previously, right? Now, last but not the least, neural networks for classification. So basically, what we can do is, just like we did in logistic regression, we can take the outputs of our neural networks essentially, and then convert it into probabilities by the means of using softmax or a sigmoid function, right? Uh, and in order to optimize it, we are using cross-entropy loss. So, by the way, how are we doing with the time?
Yeah, we are a little bit short on time, but I think you can finish.
Okay, so we have 3 minutes, right? I think.
Yeah, that's fine.
Yeah. Okay. So just a classical cross-entropy term. So essentially, cross-entropy terms is defines the relationship between one distribution respective to the other distribution. Although it is going to be a bit more complicated to explain, so I chose not to explain here. But if anybody is interested, feel free to we'll be happy to chat in the discussion part. Resources, I think, as it has already been apparent that we have run through that entire material. So it is not at all possible to go through each and every section of it and each and every granularity of any machine learning system, let alone a deep learning system. So we decided to add some resources if you wanted to satisfy your curiosity, right? So the one-stop shop is mathematics for machine learning. I think we did our first session on based on that book as well. Another one is machine learning by Kevin Murphy. So it's a really thick book, but it is a really dense book, but at the same time, it goes over a lot of material, right? Dive into deep learning, right? The one that we are currently working with. Resources, linear algebra and calculus. Grant Sanderson, I think he's pretty much the star of creating a really great basis for what is to come, especially in data science, right? So these are extremely important basics that we should all be familiar with. Another book that I truly love is by Theodore Schifrin, and it all goes over from calculus to manifolds, which is quite interesting. Probability and statistics, the one that I quite love is one by Mendenhall and Beaver and Beaver. There's also a book that a lot of people recommend is by Larry Weiserman, and all of statistics. I think I'm sure you've heard of it. There are a lot of mm, channels, YouTube channels that goes over the same material. Uh, some of them I listed here. Numerical linear algebra and optimization. So fast.ai has a really good series on numerical linear algebra. Also convex optimization. I really love this book by Stephen Boyd. And if you wanted to go deeper on non-convex and and the community that surrounds that, numerical optimization is a really good book that these guys recommend. Sorry. Information theory. So I like it is really close to my heart. This book is really close to my heart. So David J.C. Mackay. So it's a classical book if you want to go deeper into information theory. Uh, Statistical machine learning. So one can start with introduction to statistical learning, ISLR, and move to the ESL and PRML. I think this is another book that is close to my heart as well. Deep learning, of course, Grant Sanderson to the rescue again. So if you wanted to have a visual introduction to neural networks, I think this is a really good playlist that we encourage you to look into. Another one is one by Ian Goodfellow, Yashua Benjoy, and Aaron Corwell. This is a really good book as well. I think it is a standard text if you want to get deeper into deep learning, right? And last but certainly not the least, this post by guys from Berkeley. So full stack deep learning, which goes all about how can we put these models into production, which I think is a really important piece of the puzzle if you wanted to be, I don't know, a full stack deep learner or something of that sort, right? So I think that's it from my side. Now we will move on to the coding part, and I stop boring you from this point. And if you have any questions, then we will discuss it after the coding part. So please do stay till the end. And thank you so much for having me.
Okay, thank you so much, Mrityunjay, for the great introduction into the topic. Let's move on to the coding part itself. And now you should be able to see my screen, right? Can you confirm, Mrityunjay?
Yes, yes, yes.
Okay, perfect. Yeah, it's nice to be back, everyone. And now we will do 60 minutes where we will re-implement the linear regression and the MLP that Mrityunjay kindly introduced just now. And the tool we will be using is called Colab. So if you type Google Colab, you should be able to find this site, this page, or you could even from your drive, if I show you maybe my drive here, you could actually go to new, and then if you go to more, you could open Google Collaboratory, and this will basically open such a page where you can, if you're familiar with Jupyter Notebooks, you will be able, it's very similar, you will be able to insert text as well as code. And I've already prepared a notebook here that I will be filling out live. And yeah, I hope you will enjoy it. So the first notebook, there will be two, is about general components of ML code, exemplified on the linear regression that we just saw. So first and foremost, what we need to do is to install d to l equal 0.16.2. And what this will do is install the library of the book that we are discussing. So the authors kindly provided already many of the functionalities and methods that we might or might not reuse. But just for information, you can install libraries that you will want to use in Google Collaboratory, which are not already pre-installed, using this exclamation mark and then pip install the library. And as you can see here, if I look at the output of my notebook, everything seems, or a lot seems already to be pre-installed, which is kind of nice. And then it installed this D2 package. Yes, sorry.
Yeah, sorry. I was wondering if we could share the link to the collab notebook as well.
Oh, I haven't thought
So
about
you
this.
can copy it and then I think you can share it. If
But maybe then many people will work on the same notebook. I'm worried.
You
no,
can just
you
make a
can just
copy, I
copy.
think.
Yeah.
Okay, wait. So how to do that? Can you just tell?
Make save a copy in Drive and you can just share that link.
Okay, it's creating a copy. Open it in new now. But there's again this. Yeah, never mind. So here, this is the notebook, and then should I download it? Oh, okay,
You can share the link.
the link.
You can share the link. So go backwards.
Here, share.
Yeah, that's good. Uh, anyone with the link, yeah, change it to.
Yeah, but then everyone will be doing the editing
Yeah,
on
but
this.
you made a copy to it, so you don't have to worry about.
Okay, so
Everyone will be making a copy of it.
yes. Please make a copy of that notebook itself. Don't edit it directly. That would be great. Thanks. Then done. Then okay. Let me go to the chat. Shoop. And now you should have the notebook. Okay. Now you should have. Yeah, please confirm later on if there's some issues or if you cannot download the notebook. I will just continue for now. Oh, sorry, I haven't mentioned, but you can also suppress the output of the notebook by clicking on the little X, and it will just bring you back. So as I've written here, we will look into the necessary building blocks of machine learning code in general. And we will use just a very simple example to demonstrate what these blocks are and how they interplay with each other. So let's assume that we want to predict some house prices based on a data set we have. And a simple model that we can use to generate some insights will be the linear regression model that we've seen. So let's assume that the price is indeed given by some parameter W area times the actual area of one house plus some parameter associated with the age of the house times the actual age of that house plus some bias. This formula, which is written in words, so to speak, can be rewritten as here, where y hat is a prediction. In statistics, whenever or most of the time when we see hats over variables, it means that those are estimates of those variables. So here we have an estimate of our house price depending on some parameters W and some input data X. And we can even further simplify this formulation under some matrix notation. So the formula here is very simple, and it will be X times W plus B. Okay, the first thing we should do in any machine learning project and in Python in general is to import libraries. And I'm gonna import random, which will generate random numbers for us. I will import torch, which is the PyTorch library. Uh, I'm not sure if I need it, but I had it in my master notebook, so I will also import it here. And lastly, we need something to see what we're doing. So I'm gonna import matplotlib.pyplot as PLT, and I want to show my plots in this notebook. So I'm just gonna do this, and if I run here, it should import everything for me. Okay. Oh, I think I deconnected, so I have to reinstall here. Yeah, that's gonna be a bit annoying, but that's what it is. Yeah, and of course, there will always be some misspellings. Okay, now we imported the libraries. We can go on to actually generate a data set. So in this case, I don't really have a data set. So I will create one, and it's just for the purpose of having an example. So I will generate 1000 data points where the true parameters, x1 and x2, will be 2 and minus 3.4. And we will also set some bias to 4.7. And because when we collect data from the real world, our measuring instruments are not correct, or we measure at different days, we will never, ever, ever get perfect measurements. And this can be represented by a noise term, epsilon. And in our case, we will use a Gaussian normal distribution to simulate that noise that we would find in real world data. So first, synthetic data, let's create this function, and it will take a tuple W, B, and the number of examples.
Pierre, there's a suggestion.
Yes.
Can you type even slower so that
Slower?
we can, yeah, so that we can follow.
Okay.
Yeah.
Yeah, I have quite a lot. So for the purpose of time, I don't want to go too slow, to be honest, but I will try to not go crazy fast either.
Yeah. Yeah.
Yeah, but thanks for the heads up. Thank you very much. Yeah, so we are in the process of generating some synthetic data, and the idea here is to we will create the input features, the x's, from a normal distribution, and this is very easily created from the PyTorch framework using torch.normal. And I want to have, one standard deviation of 1, and the output shape should be this. And then we also are going to generate the labels. And because we have the true, we know how the labels should be, ideally, we can just multiply the parameters that we are going to give to our model times the input features that we just generated plus the bias. So this here is without noise. And then we are going to add some noise, which comes from the normal distribution, and mean 0.01, let's just say. And it should have the shape, the same shape as y, since we are adding it to the y vector. So here we are adding the Gaussian noise. And finally, we return our features and our labels, but we want to reshape it to have a single column, basically. So here I'm just making sure that my labels have the correct tensor shape. And if I run this, okay, perfect. No errors so far. So what I can do now is say my true weights will be a tensor. And I said 2 minus 3.4. And PyTorch is, yeah, this is basically the function that we need to use to generate tensors in PyTorch. So you will see that everywhere. And for the bias, we will just have a float value of 4.2, and the number of samples will be 1000. And if I call my function synthetic data with true W and true B and none samples. Okay. This should generate the dataset for us. Okay, so far so good. It seems that the code was executed by Colab. And then let's just make sure that everything is fine. This is how you would print something to your std out in Python here. So here I'm only interested in the first sample of my dataset. Basically, I just want to see the features. And if I also want to print the label, should go format labels 0. This should give me the first sample in terms of features and in terms of the labels. And tada, indeed, here we would have the x1, here we have the x2, and here we have the label, which is close to 10. So far so good, but we only checked the first sample. And since we created this data ourselves, it's a good idea to check all the data samples. And we're gonna do that by creating a figure using Matplotlib. So if I do this, plt.subplots fig size is equal to because we are creating subplots, I need to specify the number of rows and the number of columns I want to use. And one thing I discovered, I've never used Colab before, but one very neat feature of Colab is that if you hover over the definition of something, be it a class or a method, you will get the docstring, so the documentation of that method. So if you ever get lost and you would like to know more about the method or why, whether is an issue when you call that method, just hovering over it and, oh, I shouldn't have moved there. We can see what is required and what we can actually pass to all these methods, given that the docstring has been defined by the creator of that method or class. So very neat little trick, and was really a pleasant surprise to see that. I don't think that many, or Vim at least, that I'm using doesn't have that nice feature. But coming back to our code, I just want to create some figure, and I'm gonna plot yeah, the labels, and then I'm also gonna set name here. That should be X label. This will be my feature 1. And X1 set while label. This is going to be, no, that's actually going to be the label. Okay. And I'm going to do the same thing for the second feature, but I'm not going to go through the trouble of writing everything up again. And I'm just going to use some copy pasting here. And if I do plt show and plt.close, if I did everything correctly, it should show me a figure, and yes, awesome. So what we see on this figure is that for the first feature, the label is positively correlated, which is to be expected since we set the true parameter exactly in that way. And we can see that for feature 2, the parameter should be negative, right? Since the label is decreasing when the second feature is increasing. So everything seems to be more or less how it should be. So we can move on to the second part. And now that we have our data set, one common problem that we face when creating machine learning code is how do we feed this data to the model itself? And I'm just going to go here. What I need to do here is to define data iter, and it will be samples. Sorry. Batch size and the features and the labels. And that's it. And then we can get here. That's not what I wanted. Okay. The number of samples is equal to the number of features that I have, and the indices is equal to the list range non-samples. So here we are just creating a list of all the data samples that we have. And then we don't want to go through the data in a listed order. We want to randomize the data points, because sometimes in the real world, if we would measure the data points consequently, they might be correlated, and we don't want to train a machine learning model on data which is not independent. So one thing that always comes up is that we shuffle our data set in some way or another. And then range from 0 to the number of samples, batch size, batch is equal to the indices I to the minimum. So what I'm doing here is I'm creating the mini batches, which is a batch is a collection of data set that we would pass to the model. And we don't pass all of the data set at the same time. What we do is create little chunks and pass these chunks. And this function here basically is going to do exactly that. And I think I have an error here. Yes, there should be only one. Okay. And we are going to yield these data chunks back to wherever we are going to use them. Labels, batch indices. Okay, so if everything's okay here, yeah, everything seems to be nice. And if I set the batch size to 10, and features. So here I'm just going to call the function that I just defined to get some data. And then I want to print out basically what I just created. And we're going to print the shape of X. Oops. And we're going to print the shape of Y. And because it's an iterator, I just want to break here so that I'm just calling this function a single time. And yes, here it's here. Let's call it again and call it here. Nice, it worked. So we see here an example of a mini batch where this would be my data points. This will be my data points, sorry. And these are my labels. And we can see that the size here, since I asked for 10 data points, the batch size is correct. So here we have 10 samples with 2 features, and here 10 samples with 1 feature. Then we are going to define the model itself. So v is going to be torch.normal 0.01 because we want to initialize it with something. There will be 2. Basically, we have 2 parameters, so this will be the size. And really important is that we want to set requires gradient equal true because we need to be able to change this parameter later on. And then b will be torch 0s 1, and here also requires grad true. So here we are just going to initialize some parameters, and then we define the model itself, which will take x, the parameters, and the bias, and it will basically return torch.matrix multiplication. So this is the model we saw between x and w, and we add the bias. So everything okay so far? Yeah, it seems fine. Then we're gonna implement the loss function. So this is gonna be the squared loss. We're gonna have our predictions, and we need to pass the ground truths. And we basically return the difference between y hat minus y. And we're going to reshape this just in case there is a mismatch. Okay, and we need to do here square it and divide it by 2. So here we are using the squared loss function that is given here. So what's important about this loss function is that when y hat is very close to y, your loss is going to be very small. So this term here in the brackets will be close to 0, and everything is okay. However, if we are going away, when our prediction is way off from the ground truth, what will happen is that this loss is going to become huge, especially so that we have squared the difference here. Let me just run here. And then we have to define how we want to update our weights. And here I've just given the mathematical expression that we are going to use. And basically here I'm going to do def sgd and params, so the parameters and the learning rate and the batch size. And with torch.noGrad, because we don't want this to flow back for every parameter, what we're going to do is param minus equal the learning rate times the gradient of the parameter divided by the batch size, which is exactly what is this equation here. And lastly, we are going to put the gradient back to 0, because we don't want this operation to meddle with the back propagation during the propagation. Okay, and then let's define some learning rate here. We are gonna also train our system for 3 epochs, and we're gonna have some network, and our network is just gonna be this linear regression model. Forgot the equal sign here. Number of epochs is equal to 3. And we also have the loss, which will be our squared loss function here. Okay, I think I don't have, if I run this here, it should be fine. Yes, perfect. And here we're gonna go to the actual testing of the model. So for
can I interrupt really quickly? I think
sure.
some people are having trouble like following so fast. So we're just thinking, instead of maybe one large discussion at the end, can we do just intermediate, like now, for example, if people have any questions, or just quickly maybe recap the different blocks to make it easier to follow. Would that be okay?
Yeah, sure.
Yeah, another thing is, can you just copy whatever you just did up till now so that people can follow it at their own leisure?
Sorry, I couldn't follow what you said, Mrityunjay. Copy where?
Copy whatever you implemented up till now so that
Sure.
people can look at it, because of course we have time constraint to address each and every cell.
Right.
But it would be better to copy that.
Okay.
Mrityunjay, if anyone refreshes the old notebook, the notebook which Pierre posted, the updated code will be there, because he's writing in the copy session notebook only. So just update the link. Yeah.
Yeah, sorry, I didn't know about that.
Yes.
Can
Exactly.
anybody check if it's really happening? I don't know how to do that. Can you guide me through it? Whoever spoke, I don't know. Devansh, was that you?
Just refresh the link which Pierre posted in one of the new tabs, and that's it. Just open this tab. Yeah.
Yeah, that's much better.
Yeah, thank you very much for pointing that out. I didn't catch that, but indeed, I'm writing in the copy, so when you refresh it, you will get the updated code.
Yeah, that is super helpful. Thank you so much.
Yeah, thank you so much. Yeah, I'm really sorry for going a little bit too fast. Yeah, I'm more than happy to take things maybe a little bit slower, and we can discuss a little bit more into the detail. Maybe in this case,
like at each section, can you just summarize a bit so that people are on the same page? That will clear out some of the doubt and some granularity, some doubt that requires granular control. We will handle it after in the discussion.
Okay. Yeah, I would be more than happy to do that. So let's maybe recap what we're trying to do. So we are implementing the linear regression model. And what we first did is to import the libraries that we will need to achieve our goal. Because we don't have a data set ourselves, what we did is to first create a data set by ourselves. And what we did, we did that by deciding the parameters ourselves first. And then we generated these x's with a Gaussian distribution, and we also generated the labels. And the labels are very easy to generate because we already know how, we already know how these labels should look like from this formula. So all we did so far is to generate the data that we will be using to train our model on. And here what we did is to set these true parameters and the true bias. And we decided that we wanted to get 1000 samples. And I called here my synthetic data method just to generate the data. I then proceeded to check the first sample to see whether my function was actually doing what it was supposed to do. And yeah, here it gave me back one sample. So this will be, for the first sample, this will be the X1, this will be the X2, X1, X2, and this will be the label that we will be using. And we also checked by plotting out the features and the labels. We checked whether or not the data was correlated in the way we had set it up. So we can see that the first feature and the label are positively correlated, whereas the second feature and the label are negatively correlated, which is to be expected since we set the parameters ourselves. So really, there are no surprises here. What we then did, and I think probably here is where it gets maybe a little bit, I went maybe too fast, is that we need to create a method which will send the data to our model, but we don't have enough memory maybe on the GPU for a whole data set, or we are constrained. And what we can do is to create mini batches of data. So batches are just chunks of data that we pass to our model. And this is what this data iter method is doing. So it takes a batch size we want to use. It takes all the features that we created as well as the labels. And here it basically randomly iterates over the data set we created, and it will return to us some mini batches of data that we will feed into our model. So here, all I did was to check the first mini batch, as well as whether or not the size was correct of our tensor. And then we went to define the model and initialize the model parameters. So our model, if you remember, and I have it here, is defined by the W's and the bias. So what we did here is to set up the W, which, because we don't know what it is from the beginning, I mean, we do know in this case, but in the real world use case, you wouldn't know. So what we do here is to just initialize these parameters from a normal distribution with mean 0 and standard deviation 0.01. And we know that we have two features, so we want to have two parameters. This is where this size comes from. And we also say that we want to have the gradient. We want to keep track of the gradient because this is what we use to basically change our parameters. What we will do is first calculate the loss and do what's called back propagation. And back propagation will tell us, or we calculating basically the gradients, and the whole algorithm, optimization algorithm, will tell us how to change these parameters so that we are minimizing the loss. But here, all we did so far is to initialize the parameters. And here we define the model, which is a very simple model where we just do matrix multiplication between X and W, and we add the bias. Then we defined the loss function, which is the squared loss function here. So we calculate the difference between our prediction and the ground truth. We will square it and we divide it by 2. If you read the book, you will see that 1/2 or the 1/2 here can be forgotten about, because we are optimizing or we're trying to solve an optimization problem. So whether or not we divide here the loss by 1/2 or not will not really change the result. But it's just that when we take the derivative of this loss, which is the case when we do the backpropagation, this will cancel out very nicely, right? Because here the 2 will come down and cancel out this 1/2. But here we basically just defined this squared loss function. And then I was getting into, oh, sorry for that. I was getting into the optimization algorithm, which is stochastic gradient descent. And the idea here is that how we update our weights and biases is by changing these weights and biases using this formula. And what we are here doing is first calculate the loss given our current weights and bias, our current weights and the bias term. We take the derivative of this loss with respect to either the weights and or the bias, and we sum up all these terms for each sample in the mini batch, and we divide by the total size of our data set. And one important concept we didn't really explain, but what's important in optimization algorithms that we don't want to go a full step because we might go too far. So this epsilon, sorry about that. This epsilon here is called the learning rate, and it tells us, it's basically scales the update that we're moving. So as you can imagine, if this sorry, the Greek letter is escaping me right now, but if this learning rate here is very small, then our update of the weights and the bias will also be very small. Whereas if the learning rate is really big, and this term here on the right side is also big, our weights and the bias will also will be changed a lot. Yeah, so that's the basic idea of the stochastic gradient descent. And here I was implementing this method, which is implemented in these like four lines of codes. Basically what we do here is to pass the parameters, the learning rate, as well as the batch size. Here we tell PyTorch to not keep gradient of the tensor that we are passing, because we are updating them here ourselves. And this code of line here is exactly this mathematical formula. And then we reset the gradient back to 0 for the parameters. And then the second last component that we need to discuss is the training loop of the model. And for that, we are going to set a learning rate, as we just discussed. We need to set the number of epochs, so how many times we want to learn over the whole data set, which network or model, I called it network here, but it's really just a model we want to use. So in our case, this linear regression model, and as well as which loss function we want to use. So if I go back to the example and I go, and please let me know if there are any questions or if something wasn't really clear. Let me just check the chat. Okay. Then, oh, sorry for that. For X, for all the features here, and the features labels. Then we are first going to calculate the loss, and we're going to pass it through our network. Y. So this will calculate the loss on this mini batch. And here we create the prediction. And here we have the ground truth. So everything should be fine. And then we want to sum up. And here we have to call backward to calculate the gradients on, we have to calculate the gradients so that our stochastic gradient descent will work. And then we call the optimization algorithm that we re-implemented from scratch, learning rate, and the batch size. Okay, so this is good. And then with touch no gradient, here again, I'm asking PyTorch to not care about the gradients. Network features be labels. And I'm just going to print out to see what is happening in my training loop here. And I also want to print out the loss. Oh, this one should be here. And it's going to be a float. Train loss, that mean. I'm just interested in the mean value of the loss, and that should work. Okay, it's saying that labels. Yes. Here. Okay, and nice. As we can see, at epoch 1, the loss was 0.05. At epoch 2, it got lower, and at epoch 3, it got even lower. So our model is learning something, which is really nice. And we can even basically print out the loss. So error in estimating is going to be true. W minus, oops, minus V dot reshape true W dot shape. And print error in estimating B is going to be very similarly just true B minus the estimated B, right? And if I run this, okay, it seems it has worked for, oh no, it worked actually. Nice. So we can see that the error is very low for our parameters. So our system really worked. Okay, because we don't really have a lot of time, I think it's best that we don't do the live coding itself, but I show you the full code that I had. Let me, okay. So this is exactly the same thing as we had. And we can basically do everything we just did, but we can do it much more cleverly. So here we really went from scratch, but this is really not necessary because PyTorch or TensorFlow Keras or MTNext give us the tools to do much more without having to think about re-implementing everything from scratch as we did. So here's an example where we do everything more simply. Here we do exactly the same thing again, and we have the true W, true B. We generate the features and the labels from the synthetic data set. And here, one tool that PyTorch gives us is called the data loader. And the data loader will do the iteration over the data for you. So you don't have to create the data iter method that I've shown you during this session. Another nice thing is that we don't also need to care about the shuffling. So I had to call random.shuffle myself, but this is not necessary here. We can just say shuffle and is trained. So this is a Boolean value, can be either true or false. If it's true, the data loader will shuffle the data for us. And here we created basically these iterators over the data, and we got virtually the same mini batch as the one we had previously. For the network, we can define in PyTorch everything through nn.sequential, and then here we can call a linear layer with nn.linear, and here we know that we have two inputs, so x1, x2, and one label. This will be our output. We need to initialize the data, and in PyTorch we can do that by first referring to the network, then the layer. Here, I mean, because we only have one layer, it will be layer 0. Go to the weight, data, and then normal underscore, and passing here the mean value as well as the standard deviation, we can initialize our weights, and we can do the same here for the bias. And here field 0 will just put the same value everywhere, and here we decide to set our bias to 0. We also don't need to rewrite the whole loss function. Here we use the mean squared error loss. And even the stochastic gradient descent, so the complicated, the intimidating looking formula over here has already been implemented for us in PyTorch. Even more complicated optimizers have been implemented. Here, we're just showing a very simple one, and we can simply call it with torch.optim and then the name of the optimizer. So here SGD for stochastic gradient descent, but it could be Adam or any other optimizer available. Here we just need to tell the optimizer which parameters we want to update. So here it will be our network here that we defined, dot parameters. This will create an iterator over all the parameters of my network, and we just need to set the learning rate. And even for training now, there is something called PyTorch Lightning, which will simplify all these training and evaluation loops. But here we still implemented a very simple training loop where we do a number of epochs over our whole data set, and we iterate over our features and labels. One very common mistake is to forget to set here optimizer.0 gradient. And if you don't that, what will happen is that PyTorch will accumulate your gradients when you use your tensor, and you might not get the results that you were expecting. So one thing we always have to do is to reset the gradients here, calling optimizer.0 grad. Then we make the predictions with our network. We calculate the loss, and we call L.backward, which will do the backward propagation. And then optimizer.step will update the parameters for us. And if we do that, we will see that we get similar results. Our model is learning the true parameters. And here as well, I checked whether or not the error was big, and it wasn't that big. So I think we can be happy about that. Let me also just quickly talk about the MLP model. I'm really sorry, it's the first session, and we are also still trying to figure out how to do these sessions most efficiently. And yeah, definitely maybe live coding takes a little bit of time, but we can discuss this later. Okay, I'm just quickly going to talk about the MLP network. And let me just show the data set. One nice thing with Torch and PyTorch and Torch Vision especially is that it comes with pre-built datasets. So just by calling this torchvision.datasets.fashionmnist, we can load datasets from the library, and we don't need to define the datasets ourselves. And in this case, what I did is to download the fashion MNIST dataset, and I'm going to skip here. What this dataset is images of clothes or from shoes. So there are 10 categories. So t-shirt, pullover, sneaker, dress, and so on. And the goal of this model is then to classify, to correctly predict to which category each image belongs. So one way to do that, and I'm going to skip directly to the concise implementation here. One way to do that is to use an MLP. And the first thing we need to do is, because we are dealing with images and images are inherently 2D, we have to flatten the data first. And this is what this NN flatten does. So it will take all the columns of the image, or you can think of it as taking all the columns of the images and then just stacking them onto each other. And because the images have a size of 28 times 28, we pass these images to the linear layer with size 784. And we have here a hidden layer with size 256. We have the activation function that Mrityunjay talked about, which is the rectified linear unit. And this is what basically breaks the linearity of the deep learning model. It's what gives it this powerful capacities that we are using this activation function here. And after the activation function, we again pass it through a linear layer, and we scale down the 256 dimensions to the 10 categories. And here we initialize the weights of our model, similarly to what we have seen in the previous notebook. And what is happening here is we're just calling a PyTorch built-in function, which will do that for us. And we apply this method here on our network. And here, again, we just define the loss function that we want to use, in this case, cross-entropy loss. We define the optimizer, again, stochastic gradient descent. And here I just downloaded the data again, and I created this experiment loop, which is just a training loop. I can show you here. And in this loop, I'm just keeping track of the losses, the accuracies, how well my model is predicting over the experiment. And I'm calculating here the training loss and the training accuracy with this train epoch function. I'm evaluating how well the model is doing in a test phase. And then I'm returning back these metrics to my experiment. And if I plot it out, so here, this experiment function will just run the experiment for me. And if I plot out my results, what you can see here is that on the x-axis, you have the epochs, and on the y-axis, you have your accuracy. So one will be a perfect prediction by the model, and 0 will be the model isn't predicting anything correctly at all. And one thing we can see is that the accuracies slowly and steadily increase, be it the train accuracy or the test accuracy. And here the training loss is going down, which is also what we would be expecting. Okay, yeah, I'm really sorry I overreached a little bit here.